going to finish today with Chapter 3 example, okay? And I decided problem 14 might be a nice one for me to start with. It's very related to what you just saw because it involves sign diagrams, okay? Chapter 3, Section 1. Down so you can see it. Chapter 3, Section 1 is talking about polynomial functions. And by the way, when I say polynomial, the one we just did was a polynomial. When we worked, not the absolute value stuff, but when we worked with x squared plus 2x minus 3, that's a parabola. That's an example of what's called a polynomial. You're not doing any dividing. You're just, adding and multiplying these variables together. Now, suppose I gave you, some polynomial like, I don't know, g of x equals, let's say, 4x cubed plus blah, blah, blah. I'm not going to write it out. And I want to say something about it. I want to tell you that what we just did, the idea of a sign diagram can be very helpful. Now, what were the two steps for the sign diagram? We had to find what? The zeros, and then we had to use test points. You guys with me? By the way, back to the one we just did. How did we find the zeros? We did factoring. What's the other technique I said you could use? Quadratic formula. But here's the thing, guys. The quadratic formula works for degree 2 equations, quadratic. Can I use the quadratic formula if it's an x cubed thing? No. So you're out of luck unless you can factor. And factoring's hard. So I really like what Dr. Stitz and Dr. Ziegert did with this. They did the problems in section 1 and they said, hey, don't factor it, we'll factor it for you. Okay? So the one I picked was number 14. And they said, for number 14, it looks like this. G of x equals 2x plus 1 squared times x minus 3. That's what they said. So they took this function, and they actually did the hard work. They factored it. You guys see that? Okay. But what we're going to do is we're going to draw a little sketch of what the function looks like. And I'm not talking with the graphing calculator now either. I'm saying that I can use this procedure. So right away, can you tell me what the zeros are? Well, since it's factored, I can. See how last time I knew right away, where was my factored form? There it is. Negative 3 is a 0, and positive 1 is a 0. You guys with me? So how about this problem? When it's like this, I have no idea. But when it's like this, can you give me something that is a 0? 3, absolutely. 3 is one of the zeros. So let me plot that. Right there, 3. 3 comma 0. Can I have another 0, please? 2. See, the way you get them is this. X minus 3 could be 0. That'll make the whole thing 0. So x is 3. So for the other one, yeah, I have to work it out. 2x plus 1 is 0. 2x is negative 1. So what could x be? Do you see it? Negative 1/2? Does that make sense? Cool. So over here, I'm going to go negative 1/2 is one of the zeros. All right? Now, I want to do a sign diagram. So I draw a number line. I throw the zeros on there. So let's see, we have 3 and we have negative 1/2. Those are where it equals 0. And all I want to know is g of x positive or negative in these little intervals? That's what I want to know. So give me some test points that would be good to try. You just can't pick these. Pick any other number. 1 is a great one. Although, what's my favorite? 0, because it's so easy. I'm going to do g of 0. Remember, g of x, as written over there, is 2x plus 1 quantity squared times x minus 3. If I plug in 0, I get 1 squared times negative 3. Are you with me? But actually, that's more work than I should have done. I don't care what it equals. All I care about is the sign. This is positive, and this is. So what can you tell me about g of 0? Negative. And if it's negative, I can just write down here that the function is going to be below the x-axis down here somewhere. Okay? It's negative over here. Okay, let's take a point greater than 3. Give me something. How about g of 7, right? Well, I get positive, and I get a positive because 7 minus 3 is 4. You see that? So over here, we're positive. We're going to be above the x-axis. Are you with me? Okay, what else should I try? G of, help me out. Negative 2 is a great one, okay. So here, look what happens. This is interesting. You plug in negative 2. You get negative 4 plus 1. You get negative 3, but then what are you doing to it? Squaring it. You see that? And over here you get negative 2 minus 3. So what do I get? Positive times negative. What do I get? Negative. So that means it's negative over here. So this is a very interesting sign diagram. What happens is this curve starts, on the right side it's positive, but everything over here is negative, and everything past here is negative. So it must be that it kind of just barely touches that point, 0. You see that? And now here's where the graphing calculator is so powerful, which is why if you don't have one, I'd encourage you to use what I have on Blackboard as an external link. Here. Let me punch mine up. You can check all the mathematics we just did on this sign diagram in the following way. I'm going to type in this function. Let's see, open parentheses. 2x plus 1. Close parentheses. And then I want to square that. And then I want to multiply by open parentheses x minus 3. Close parentheses. And I say, I wonder what the graph looks like. Boom. Does it match what I did? Well, kind of is right. Mine's not to scale, Like if I were to take my y-axis and stretch it out, these values are much lower than what I had, aren't they? But I did capture some of the essence, because if you look, here, let me zoom in so you can see. It just barely kisses the x-axis right there. You see that? That's what I was talking about. It can't go above it. All right, we're out of time. Nice work today.
All right, guys, we want to find zeros. So let's see. When it says I should find zeros, Well, okay, I set the output equal to 0. And I'm very lucky because this one's already factored. I told you guys that's not usually the case. But since this is factored, what are the zeros we're going to get? X equals 0 or x equals -2. Okay? So there's the zeros. Now, there's something called multiplicity. Do you guys get that? Yeah? This one would be multiplicity what? 3. And this one would be multiplicity 2. And one question you might ask is, why? Why do we care about multiplicity? That answer comes at the end of this week. You got to be patient on it. I mean, who cares? The answers are still 0 or -2. Well, it does matter. Multiplicity does matter, and I'll get to that, but we have to be patient. All right, but the question you guys had was about sketching a graph, right? So I want to sketch a graph. I want to get a rough sketch of what it looks like. And so the idea, and I only was able to do one example last week of this, was that we have to construct something called a sign diagram. This is our first example of this, except they did them in section 2.4, but we didn't work very hard on that section. All right, so I'm going to draw a number line. And what important points do you think I'm going to put on my number line? Yeah, the zeros, right? So let's put 0 here, and let's put -2 here. And what I know is I know that h of -2 is 0, and I know that, I'm sorry, big F, not h. Big F of -2 is 0, and I know that big F of 0 equals 0. And I'm realizing this is tough for you guys to see, so we're zooming in. Okay, hopefully that's a little better. Okay, so now we want to do what are called test points. And this, I think, was the question. But what I do here is I'm going to use some test values. Test values. Now, what values are we going to test? Well, you want to pick some numbers from the different intervals. Each of the intervals. Okay? And so, what do you think I'm going to pick? I don't know. How about we pick, give me a number over here somewhere. 1 or 3 is fine. I like small numbers, so I'll use 1. And then here I'll use -1. And here I'll use what? -3? Okay. I guess I could have used 3. I mean, I'll do that one too, just to show you guys what's going on. And what I want to do now is I want to compute f of these different values. Okay? Now remember, what we're graphing is f of x is x cubed times x plus 2 squared. And so, for example, I'm going to compute f of -3. And I'm going to tell you something. I really don't care what f of -3 is. I only care about one thing. You know what that is? If it's positive or negative. The reason this is called a sign diagram is because I'm trying to decide, is f of -3 positive or negative? Well, let's see. It's going to be -3 cubed times -3 plus 2 squared. Are you with me so far? So it's -27 times -1 squared. Are you with me? Now, I could keep going. But what I really care about is if it's positive or negative. So you know what I'm going to do? I'm just going to write down that this is negative, and this one is, what happens when you square -1? Positive or negative? And if I have negative times positive, what do I get? negative. So f of negative 3, f of negative 3 is negative. Remember that f of negative 2 is 0. Hopefully this is making some sense. Here, I'm going to pause and have you guys try f of negative 1. Let's see. I'll do it here. F of negative 1 would be negative 1 cubed times negative 1 plus 2 squared. So that's negative 1 times positive 1, right? So again, it is what? Negative. So f of negative 1 is negative. Huh. How about f of 1? If I put in a 1 into this, you know what? I don't even have to write it out. I can just kind of look for this one. 1 cubed times 1 plus 2 squared. I don't see any negatives anywhere in the whole thing. So f of 1 is going to be what? Positive. What about f of 3? F of 3 is positive, right? Reminds me of my chemistry joke. Did I tell you guys that one? Did I? You don't know the chemistry? It's my only chemistry joke I know. How many of you take chemistry? Or have taken it? All right, so, you ever heard this one? Hydrogen and helium. They're walking down the street. After a while, hydrogen looks at helium and says, "Oh, man, we got to go back." Helium says, "What? Why we got to go back? What's wrong?" He goes, "Oh, I can't believe it. I got to go back. I think back there, I lost an electron." Helium says, "Well, wait, before we go back, are you sure?" Hydrogen says, "Yeah, I'm positive." All right. Well, that's recorded? That's awful. All right. Now, back to the graph. So, the reason that this sign diagram works is because polynomials are, and the word is, continuous. There's the word. What does that mean? It means I can draw the graph with one stroke of the pen. That's a weak definition. But it's actually good enough for this class. If you take calculus, you'll get a real definition of continuous. But for us, it just means I can draw it with one stroke of the pen. Which means, hey guys, look at this. Suppose somewhere over here, like at negative 1, I'm negative something. I'm actually at negative 1, right? And suppose somewhere over here, like at 1, I'm positive. Well, guess what's going to happen somewhere between negative 1, somewhere where I'm negative, and somewhere where I'm positive? What's going to happen? You've got to cross the axis, right? And so if I'm trying to sketch what this thing looks like, just a rough sketch, okay, what I can do is, first of all, I can graph the zeros. Now, where are the zeros? We said they're at 0 and negative 2. This is negative 2 and negative 3. And then I kind of take a look and I say, well, from here on out, this thing is positive. So it's growing. Over here, the thing's negative between 0 and 2. And also over here, it's negative. So this is going to be down in the negative region. It's going to come up. But I claim that as soon as I get towards that side of negative 2, we're also going to have it's negative. Because if it's negative here, it can't be positive anywhere in the interval. Otherwise, we would have had a 0 somewhere. If it's negative in the interval between 0 and 2, it has to be negative the entire way. It can't be positive anywhere. Do you guys follow this idea? See, if you think it's positive somewhere, like up here, I'm going to argue. I'm going to say, no, it's negative at negative 1. And if it were positive up here, somewhere in between, we'd have to have a 0. And we don't. We know where the zeros are. We know the only places it's going to cross the x-axis. That helps me get a sketch. Now, some of you were asking about multiplicity. Remember how this had some multiplicity? You don't know this yet. But one of the things that's going to do is that's going to make it possible that maybe I have like a little relative, what is that, by the way? A relative what? Oh, we had this word on the last chapter. Relative maximum. Do you guys remember this? Or local maximum? What do we call it? Local maximum. That's the problem. Local maximum. Relative maximum is another word for that. So that's what you call, is that a global maximum? Or not? Is that an absolute maximum for the whole function? No, because we can get as high as we want this way. The end behavior goes to infinity as x goes to infinity. But this is what you call a local maximum. Okay? So the multiplicity signals that that might happen. Not that it has to happen, but that it might. That's about all you could probably do right now, other than to compare to the actual graph. Nice. Delaney, thank you. I can't pepper.